Welcome to Context. This is Brad Harris. Today, we're discussing a book that seeks nothing less than to capture humanity's greatest ideas. If civilization collapsed and people in the future could rediscover a single work to get humankind back on track scientifically and technologically, this book would be a contender. Peter Atkins' Galileo's Finger, The 10 Great Ideas of Science, published in 2004. If you value the show and you'd like to get bonus content, head to patreon.com/context, and for as little as $1 an episode, you're in. I just uploaded another bonus episode, in fact, a great conversation with fellow historian Daniela Bellelli, host of the very successful History on Fire podcast. We discuss the changing culture of academia, deep time, martial arts, the future of history, lots of stuff I hope you'll enjoy. Patreon has a great app that you can download for free to make listening really easy. But, if you happen to have another favorite podcast player, you can grab the RSS feed from my Patreon page and input it into your podcast player to stream the Patreon content there. Again, that's on patreon.com/context. You can learn more about the show and find other ways to support it on my website, bradharris.com. And now, for Galileo's Finger, The 10 Great Ideas of Science, by Peter Atkins. It's strange to think there used to be a time when an individual could reasonably expect to know most things. What I mean is, up until a couple of centuries ago, it was not unusual for intelligent and highly educated people to be able to speak with authority on practically every scientific subject, from geology and mathematics to chemistry and physics and economics. These individuals were called polymaths or Renaissance men, but they've mostly disappeared from our world, subsumed by the flood of modern knowledge. Science has proven such a prolific tool of learning that even the most intelligent and educated among us have been forced to retreat into specialization. So, whenever someone does come along these days whose acumen echoes the expanse of the lost polymaths, we should pay careful attention. Peter Atkins is one. He may be among the only people alive today who could give a full academic lecture on chemistry, classical and quantum mechanics, thermodynamics, molecular biology, evolution. Take your pick. He earned his PhD in chemistry from Oxford in 1964, but he has honorary doctorates from a handful of other institutions. He's written at least 9 academic textbooks and well over a dozen science books for general readers, and he's racked up more intellectual awards than I can list. He also has an infectious sense of humor. Let's just say that if the scenario in the movie Contact were real, where the aliens send blueprints for a pod that will take one human through space to them, and Jodie Foster's character, a scientist who works for SETI, ends up making the trip to represent our species in the intergalactic meet and greet. You know the movie. If that were real, Peter Atkins would be on my short list for humanity's ambassador. Perhaps a slightly more realistic prospect than alien outreach is the collapse of our civilization. And should that ever happen, this book, Galileo's Finger, would become one of the most valuable guides to resurrecting it. First, we should address the name of the book. The subtitle, The 10 Great Ideas of Science, describes the book's subject. But why Galileo's Finger? Well, as anyone who's visited the Florence History of Science Museum in Italy will know, Galileo's actual finger, indeed his middle finger, is on display there, preserved in a glass sphere, an exhibit many consider as a kind of historical diss to the Catholic Church that imprisoned him for challenging religious dogma by establishing modern science. It's an apt symbol for this book, then, for as Atkins points out, quote, Galileo marks the turning point when the scientific endeavor took a new direction. He developed the art of simplification, the isolation of the essentials of a problem. He set aside the creaking cart pulled through the mud. Instead, he considered the simplicity of a ball rolling on an inclined plane, a pendulum swinging from a high support. The isolation of core phenomenon from the creaks and confusions of reality is a key part of the scientific method. In short, this book celebrates the effectiveness of Galileo's symbolic finger for pointing the way to truth. End quote. As a professional scientist and science educator, Peter Atkins, who's now in his late 70s, has spent most of his life trying to communicate not just the ideas of science, but the grandeur of a scientific worldview, the wonder of our mind's ability to know the world through rational inquiry. If there are miracles, Atkins would argue that they are not found in the surreal conjectures of things unexplained, but in the tangible power of our otherwise small minds to achieve cosmic insights through experiment and mathematics. In Galileo's finger, he distills his choices for the most profound of those insights, specifically the 10 revelations of science that have done the most to empower us. Quote, "My aim has been to identify the ideas that illuminate and, in most cases, provide the foundation for technological advance, ideas that are simple, but out of which spring a whole range of understanding, ideas that had to be like an acorn, which if you plant in fertile minds, grows into a forest of understanding." End quote. From all the centuries of effort to understand nature, all the time and money spent and sacrifices made to emancipate ourselves from ignorance and suffering, what are these acorns that qualify for inclusion in Atkins' intellectual survival guide for our species? Well, as one might expect, the scope of ideas he features is mind-boggling, spanning molecular biology to space-time, but he begins sensibly enough with what is widely considered to be the best idea humanity has ever had, which accounts for nothing less than the emergence of life's complexity. The first great idea of science Atkins presents is that evolution proceeds by natural selection. The structure of Atkins' book is simple. Each chapter is devoted to explaining each one of his great ideas. What distinguishes the book, though, is how he integrates each individual explanation into a more coherent history of science that sets it apart from other systems of knowledge, such as philosophy and theology. For example, beginning with the idea that evolution proceeds by natural selection, he writes, quote, "As so often in science, the first step towards true understanding, rather than fanciful speculation, is the collection of data, which in this case means identifying and classifying all the types of organisms that constitute the biosphere, or at least as many as patience, persistence, and providence allow. The most useful names recognize relationships, and by the middle of the 18th century, with international maritime trade established, even stay-at-homes had become familiar with the plethora of animals that populated the world, and had realized that simple names such as cow and dog were inadequate." End quote. This puts the achievement of Carl von Linnaeus into context. Most of us were simply forced to memorize the name Linnaeus by our high school biology teachers, but Atkins helps us understand why this Swedish botanist is immortal. In the 1750s, he introduced one of the most important structures of thought in history, binomial nomenclature. Homo sapiens, Tyrannosaurus rex, this scheme of names replaced arbitrary labels like man and monster to rationalize our understanding of the relationships between species, classifying them into a hierarchy of similarities and differences that would become a pillar of Darwin's theory of evolution by natural selection presented in 1859. It all relied on meticulous data collection to cut through traditional assumptions. So important was Linnaeus's binomial nomenclature for the foundation of modern biology and ecology, for modernizing our interpretation of nature, that contemporaries like Jean-Jacques Rousseau described him as the greatest man on earth, and Johann Wolfgang von Goethe wrote that few had influenced his outlook on life more strongly than Linnaeus. Without putting in the hard work to collect so much data to identify and classify organisms, the idea that evolution proceeds by natural selection could never have even gotten started. Linnaeus plowed the road for Darwin. Data collection, experiment, these often tedious, lonely labors are critical starting points in separating truth from fiction and identifying patterns in nature. And they alone pointed the way to Atkins' second great idea. Inheritance is encoded in DNA. Despite the tremendous progress made in understanding evolution in the century and a half after Linnaeus, scientists remained ignorant of the mechanism for inheritance, and this lingered as an Achilles heel to the theory of natural selection. Quote, "Despite Darwin and his contemporaries' grasp of the natural world and their profound insight into the consequences of competition, the most favored mechanism of inheritance at the time was blending inheritance, in which each parent poured their heritable characteristics into a pot that was to be their child, and the child emerged from the mix." End quote. This wasn't a theory. Theories emerge from evidence, and there was no real evidence to support blending inheritance. It was just a notion, a guess, no better than what had been on offer for thousands of years about how heritability worked. As Atkins highlights, quote, "Aristotle himself, though admirable in his pursuit of questions, had likewise gotten the answer wrong, demonstrating once again the failure of armchair speculation unsupported by experiment." End quote. Indeed, where a legitimate theory actually came from grew out of the humble experiments by a forgotten Austrian monk named Gregor Mendel, who spent 7 years crossbreeding the common garden pea between 1856 and 1863. Animal and plant crossbreeding was an ancient practice. Dogs, for example, had been purposefully bred for millennia to develop desirable characteristics. But Mendel made a science of crossbreeding by isolating 7 specific characteristics of his pea plants, including height and color, crossbreeding specific varieties, and then quantifying the resulting generational ratios of expressed traits. This was just like what Galileo had done, isolating the physical phenomenon of uniform acceleration using inclined planes, and it revealed new patterns of heritability to Mendel that no one had been able to see before. He described these patterns in terms of dominant and recessive traits, and with his hybridization data, he could predict the expression of traits with perfect accuracy. Accurate prediction, of course, is the measure of any sound science, and the incredible implications of Mendel's predictions were revealed once technology caught up with his science and allowed investigators to see chromosomes in action using microscopic dye at the turn of the 20th century. At that point, quote, "Biologists had come to suspect that chromosomes were the instruments of inheritance. Those chromosomes came into step with Mendelian inheritance in 1902, when a graduate student working in Columbia University found that paired chromosomes did indeed separate, with one member of each pair going into a different cell. At this stage, investigators could infer that Mendel's genes were carried by chromosomes. The world was ready for a new science, and in 1905, the term genetics was suggested." End quote. By this point in his narrative, Atkins has thoroughly demonstrated one of the essential features of science. Careful collection of data is hard work, but it's the only reliable way to guard against the delusion of convenient assumptions. Unscientific beliefs are often lazy, in his view. It's easy to look at nature, especially the beauty of biological structures and relationships, and just assume that they must have been designed by something supernatural. That way, we don't have to think about it anymore, he argues. As Atkins elaborated in an interview, quote, Science is extraordinarily hard work and intellectually rigorous and demands the union of minds across the world and across time to ferret out explanations that are deeply buried beneath phenomena." End quote. Our modern understanding of life's complexity as the emergent beauty of evolution is a perfect example of this. As he proceeds with the next great ideas in his book, however, his focus shifts to another essential feature that distinguishes science, its comprehensive explanatory power that comes from being quantitative. Anyone can propose qualitative ideas about how this or that part of the world works, describing the qualities of things according to their particular fancy. But only by anchoring explanations of the world to mathematics, only by providing quantitative descriptions of nature, can we have any hope of pinpointing universal laws. This is where science's unrivaled explanatory power really comes from, and this is why his chosen great ideas of science can be like acorns that grow into forests of understanding. This is also clearly manifested in his next group of great ideas. Atkins' third great idea of science is that energy is conserved. Not surprisingly, it originated with Galileo's inclined plane experiments in the early 1600s. Basically, all Galileo really did was roll a ball down an inclined plane a whole bunch of times in different ways and observe its behavior. Patterns became obvious. In particular, he saw that once a rolling ball had gained speed down an incline, that speed was preserved once the plane leveled out flat. Were it not for friction, Galileo realized, the ball would just roll on at its attained speed forever on a flat surface. Quote, Galileo realized that there are essential components of behavior on one hand and extraneous influences on the other, which include friction and air resistance. By reducing them, by polishing the ball and the surfaces of the planes, for instance, he could edge towards ideality and the exposure of essential behavior. End quote. In everyday experience, things often happen too fast to see. And combined with the chaos of the world, the wind and the mud and the rough edges of nature, the essential physics of what's really going on are totally overwhelmed. Galileo's genius was to devise experiments like the inclined plane to slow things down and reduce chaos in order to reveal those physics. By doing so, he was able to describe the essential physics of rolling balls and all sorts of other events, the physics of motion, in ideal terms, which is to say mathematically. In the late 1600s, Isaac Newton refined Galileo's mathematical observations into his 3 laws of motion, which state that a body maintains uniform motion in a straight line unless a force acts on it, that the acceleration of the body is proportional to the force applied, and that to every action there is an equal and opposite reaction. These laws formed the basis of classical mechanics, and for all their simplicity, they accurately predict the motion of balls, particles, planets, and spaceships. But it was the third of Newton's laws that held the most promise. As Atkins explains, quote, Newton's third law is deeper than it looks. The real significance of the third law is that it implies a conservation law. A conservation law is a statement saying that something doesn't change. That might seem to be the most boring kind of comment possible in science. In fact, it's commonly the deepest and most significant type of scientific law because it gives insight into the symmetry of systems and even into the symmetries of space and time. End quote. What this means is that Newton's third law equipped humanity to understand not just how discrete objects like a single ball or a planet behave, but how whole systems of objects behave, how the give and take of matter in motion proceeds, how force ripples through nature. It equipped humanity to understand the effects of pressure and temperature on whole collections of particles, just like those found powering the pistons of the Industrial Revolution a century later. In other words, Newton's third law prepared us to understand energy, a concept that matured with the development of steam engines through the middle of the 1800s. And by recognizing that energy is always conserved and never destroyed in any system, humanity had discovered a unifying principle underlying not only mechanics, but magnetism, light, electricity, biology, and even space and time. The steam engines of the Industrial Revolution helped teach us much about energy. They provided real-life examples of the principle that energy was conserved, in particular by demonstrating how, instead of being destroyed, energy was transformed by steam engines from heat into work. This proved to be one of humanity's most important insights, illuminating an entirely new branch of science called thermodynamics and leading to Atkins' fourth great idea, that all change is the purposeless collapse of energy and matter into disorder. This idea, otherwise known as entropy, is leveraged in practically all of the machines that now power our modern lifestyle, from the steam engines and steam turbines of our power plants to the jet engines and internal combustion engines of our transportation. But it's an idea whose implications go much, much further. Entropy, the principle that the things of this world, the matter and the energy comprising them, tend toward disorder, actually erupts with scientific potential. There's an irony here, of course, which Atkins interprets well. Quote, "Now, you might consider that there are certain difficulties with this bleak worldview. If the direction of the universe is towards degradation, what room is there in it for the emergence of exquisite structures, of people, and of noble thoughts and deeds? To resolve this paradox, the crucial point to grasp is that no change is an island of activity. Change is a network of interconnected events. Although drift into degradation might take place in one location, the consequence of that drift might be to ratchet up a structure someplace else." End quote. Once scientists fully grasped this truth, they began to see everything differently. The emergence of life itself, for example, assumed new coherence with the cosmic accountancy of thermodynamics. Quote, "The ceaseless decline in the quality of energy expressed by entropy is a spring that has driven the emergence of all the components of the current biosphere. In a very direct sense, all the kingdoms of creation have been hoisted out of inorganic matter as the universe has sunk ever more into chaos." End quote. Reading such passages, one is suddenly struck by a new perspective on the emergence of complexity in our world. If only for a moment, Atkins helps us to imagine life as the manifestation of a great waterfall of energy, gushing from the fount of fusion in our sun as its own energy and matter decay, and upwelling from there through the photosynthetic springs of forests, flowers, and fruit here on Earth, flowing on through countless animals and even unto the trickling of thoughts that arise in our brains. It's all connected and beautiful and so much bigger than us, though it animates the smallest things we can imagine. Quote, "The molecular basis of life also springs from entropy. Life is a process in which molecules bumble around, just happening to have the right shape to fit in a niche, and able to release their burden of energy in turn. The concept that complexity is fabricated from simplicity was a profoundly important conceptual step, and this attitude still lies at the core of modern science." End quote. It also confirmed the fifth great idea of the book: matter is atomic. For thousands of years, philosophers speculated on the nature of matter, and one of the guiding questions was whether matter was continuous or discrete. Was there some fundamental element or set of elements comprising everything, beyond which no further division was possible? Or could matter be endlessly sliced into smaller and smaller pieces? According to Atkins, to make the study of matter scientific, quote, The balance turned out to be the key. In the hands of the French chemist Lavoisier in the late 1700s, who's widely regarded as the father of modern chemistry, the chemical balance became the scalpel that could be used to cut deeply into the mystery of matter. Carefully and thoughtfully deployed, the balance could be used to attach numbers to matter and bring chemical reactions into the realm of arithmetic. End quote. What the balance provided that no philosophy ever could was a means to measure matter precisely for the first time, enabling investigators to discern the masses of substances, both in isolation and after reacting with other substances. As a consequence, quote, patterns began to emerge in the data, and as we've already seen, patterns are the lifeblood of science and the seeds of theories. The pattern of the masses of the elements that combined together was the acorn that grew into the oak tree of Dalton's atomic hypothesis. End quote. Based on the patterns he saw in the numbers, the English chemist John Dalton in the 18-teens organized the known elements into a list of their relative atomic weights compared to the hydrogen atom, which he designated as having an atomic weight of 1. By quantifying matter in this way, Dalton provided the theoretical framework for modern chemistry that led later investigators to recognize all sorts of other patterns, not least of which Dmitri Mendeleev, who first proposed the periodic table of the elements in 1869. The brilliance of the periodic table was in manifesting these patterns so clearly that it implied not only the properties of elements yet to be discovered, but it also suggested deeper properties, guiding how the elements combine into larger arrangements of matter. One of those properties is something called symmetry, and this represents Atkins' sixth great idea of science, that symmetry limits, guides, and drives the structure of our world. Symmetry is one of the properties of nature that not only make the world more predictable and comprehensible, but that also make it beautiful. It's just what it sounds like. The arrangements of matter, from molecules to maple leaves, naturally tend towards some kind of symmetrical geometry, mirror image components, as it were, so that if you slice them in half or into some other even set of fragments, you'd get near identical pieces. Indeed, symmetry begins all the way down with the structure of molecules, and as chemists' understanding of symmetry advanced through the 1800s and into the 1900s, they began to see just how powerful a tool of prediction and comprehension it really was. Symmetry has become a fundamental concept in chemistry that enables scientists to predict all kinds of chemical properties, including polarity and reactive potential. Theoretical chemists rely on symmetry to model catalysts, drug delivery, biomass conversion, and more. Beyond chemistry, symmetry inspires much of mathematics, as well as art, music, and design. What really captivates Atkins about symmetry is the elegance that emerges from it. Quote, "We resort to the mathematical aspects of symmetry and the symmetrical aspects of mathematics to build our understanding of the fundamental entities from which matter is carved and the dynamical counterbalance of the forces that hold these entities together. Could it be that beauty is the key to understanding this beautiful world?" End quote. This is the kind of insight that captivates scientists, and that can make a scientific understanding of the world at least as awe-inspiring as any theology strives to be. We should relish such intuitive, satisfying paths to knowledge. For, as Atkins goes on to show, some of the most profound discoveries about how the world actually works turn out to be extremely counterintuitive. This is particularly true at the most fundamental level of matter and energy we've probed, and here we encounter Atkins' seventh great idea of science, that waves behave like particles, and particles behave like waves. Quantum mechanics. It's been around for over 100 years now, and scientists have grown very comfortable with the theory, using it to make all kinds of predictions and integrating it into all kinds of technologies. Atkins highlights that no less than 30% of the GDP of the United States depends on the applications of quantum mechanics in some form or another. No other theory of matter has proven so robust. Nonetheless, quantum mechanics is bizarre. Quote, "The problem is that although we can use the theory with great skill and authority, despite 100 years of argument, no one quite knows what it all means." End quote. Quantum mechanics is where science forces us to disregard our instincts and rely mostly on mathematics to guide our comprehension. It's difficult to fully convey how the discovery of wave-particle duality in the early 1900s culminated in quantum mechanics without mathematical and graphical diagrams, but Atkins nonetheless uses this great idea to exemplify how science, if we dare to follow, can lead us to insights we could never imagine. Briefly put, through the 1800s, scientists began to recognize certain phenomena in nature that did not behave according to classical mechanics. Black body radiation, which is the energy that radiates off a heated object, was a particular problem. When carefully measuring the radiation emitted from an object, like a piece of metal as it was heated up, it became clear that the emitted radiation did not increase continuously, rising through the visual spectrum, for example, from red hot to yellow to white to blue as it appeared to do. Instead, the actual frequency of the emitted radiation jumped from one discrete level to the next. These discrete jumps were way too small to see with the naked eye, of course, but they were there, and they completely contradicted classical mechanics, which would predict a smooth, continuous increase in emitted radiation as the object was heated. This mystery lingered for years, and it was like finding an exception to something as solid as gravity. More on that later, but imagine finding a particular kind of stone that just floated. Every other stone you've ever encountered falls like stones should, but this one stone defies the laws of physics as you know them. That's akin to what confronted scientists at the end of the 1800s, and Max Planck, a German physicist, finally proposed an explanation in 1900 which undermined everything we thought we knew about matter and energy. Quote, "Planck's revolutionary, crazy idea was that energy came in lumps, that it's granular rather than smooth, that it is as sand rather than water, an idea that was to transform our perception of reality." End quote. Planck was arguing that energy is not continuous but quantized, flowing through nature only in discrete packets. To use a more modern analogy, it was like asserting that reality was in some sense fundamentally digital rather than analog. Now, at first, no one in the scientific community really knew how to feel about Planck's argument. But as the next couple of decades rolled by, and other scientists like Einstein, Louis de Broglie, Werner Heisenberg, and Erwin Schrödinger tested Planck's ideas, it became clear that he was right. And some of the most convincing data stemmed from experiments on the nature of light. The consensus prior to that time, through most of the 1800s, was that light consisted of waves. But new experiments in the late 1800s and early 1900s had demonstrated that light could also behave more like a stream of particles. So, right in the middle of the uproar over Planck's assertion of quantum mechanics, physicists were stuck trying to understand the apparent wave-particle duality of light. Planck's quantum theory gave them a new mathematical tool to test this prospect, not only with light, but with the full range of subatomic particles, such as electrons. Once they did that, physicists realized that not only light, but all matter exhibited both particle and wave-like properties. This was the key to convincing the scientific community that quantum mechanics was true. Once physicists discovered that not only energy but matter behaved like waves, they realized that measuring particles, locating an electron in space, for example, was really just an exercise in measuring the amplitude of waves corresponding to those particles, to that electron as it traveled around in our example. Wherever the amplitude was high, they were likely to find the electron, and wherever the amplitude was zero, there was no chance of finding it. As Atkins describes, understanding waves enabled physicists to understand the location of particles in quantum theory. And since peak wave amplitudes are themselves discrete, which is to say quantized, just like the crests of waves on the ocean occur only at certain locations and are not spread out continuously, interpreting the behavior of energy and matter in terms of waves enabled scientists to see the truth of quantized energy and matter. The frequency of black-body radiation, the vibration of a string, the swing of a pendulum, all demonstrate discrete, quantized states of energy. As Atkins writes, quote, "It is certainly the case that macroscopic objects behave to a very good approximation in accord with classical physics. But we know that that behavior is simply the manifestation of quantum mechanics applied to large numbers of atoms." End quote. That waves behave like particles and particles behave like waves remains as counterintuitive today as it was when Max Planck hinted at the concept over a century ago. But this idea has proven to reveal more about the underlying behavior of matter and energy than any other that humanity has come up with. The next couple of ideas that Atkins puts forth strengthen his point that science can lead us to insights about the nature of the universe well beyond any that human minds could otherwise conjure. Indeed, Atkins' eighth great idea of science is that the universe is expanding, which in turn implies that it actually had some kind of beginning. Our advancing knowledge of our place in the universe is one of the most humbling developments in human history, but it's also one of the most inspiring, for it suggests that our otherwise feeble intelligence may have limitless potential through the discipline of science. Quote, "The inescapable and ironical humiliation is that each astronomical and cosmological revolution has diminished the uniqueness of man's position. Ptolemy had us at the center of the universe. Copernicus nudged us to a beautiful but nevertheless minor planet in orbit around the sun. Since then, the sun has been elbowed out to an insignificant location in an insignificant galaxy, in an insignificant cluster, in what may prove to be an insignificant universe. Yet, at the same time as we have been forced to realize our insignificance, we puny-brained little things have grasped the extent of the universe, have put a measure on all there is, have identified what seems to be our origin, and have even found out the likely unfolding of our cosmic future. It is right that we be proud in the midst of our ceaselessly increasing humility." End quote. The idea that the universe is expanding was deduced mainly through the work of two American astronomers in the early 1900s, Henrietta Leavitt and Edwin Hubble. When Hubble first looked through a telescope in 1919, everyone thought that our Milky Way galaxy represented the entire universe, and the scientific community had been busy for years working out the distances to all the observable Milky Way stars to determine the size of the known universe. To do this, they relied on a technique pioneered by Leavitt that she had based on the oscillating brightness of a particular kind of star called the Cepheid variable. Leavitt's measurement had become a kind of standard astronomical mile marker, and Hubble began using it to try calculating the distance to a different sort of celestial object, not stars, but fuzzy patches of light called nebulae that astronomers weren't quite sure what to make of. Working off of Leavitt's calculations, Hubble's conclusions about the distance to nebulae was shocking. Quote, Whereas our own galaxy, the Milky Way, was known to have a diameter of about 25,000 light-years, the closest of these nebulae, the Andromeda Nebula, was about 2 million light-years away. It had to be outside our galaxy. It was another galaxy. Immediately, the perception of our universe became bigger than had previously been believed, and the rack of our humiliation was stretched another notch. End quote. Atkins has such a way with words, but he quickly proceeds to describe Hubble's more monumental conclusion in 1929. Not only were there other galaxies, but by elaborating upon Leavitt's mathematics using the variable brightness of Cepheids, Hubble was able to calculate that those galaxies were actually receding from us. As Atkins summarizes, quote, "The implication of this expansion is awesome. For if we trace it back through time, then there must come a moment when the universe itself is a single point. That is, the universe seems to have had a beginning." Hubble's astronomical legacy is the experimental discovery of the expansion of the universe. His intellectual legacy, however, is greater, for it is nothing less than the realization that we can trace our history back almost to the beginning of time. End quote. By this point in his book, Atkins' argument is nearly complete. He has one more great idea to showcase science's unique power to unlock the mysteries of the universe before he culminates the entire list with the idea that forms the backbone of them all. The ninth great idea of science, that space-time is curved by matter, actually sets him up to finish the book with the 10th and final great idea, which is, simply put, mathematics itself. This is because the idea that space and time are not only bound together, but also curved by matter, is one of the best examples of all of mathematics' brute force revelations. Practically everyone who'd ever thought seriously about space and time, from Aristotle to Newton, concluded that they were absolute entities. As Newton himself wrote, quote, "Absolute space, without relation to anything external, remains always similar and immovable, and absolute time, of itself and from its own nature, flows equally without relation to anything external." End quote. And yet, precisely because Newton was one of the most gifted mathematical thinkers who's ever lived, these absolutes caused him a lot of trouble when it came to gravity, since he could not find a good way to mathematically connect gravity to absolute space and time. As Atkins writes, quote, "The concept of action at a distance, that a star could wrap the path of a distant planet into something akin to a circle, was deeply puzzling to Newton, who saw that it was a defect of his theory." End quote. In other words, gravity's action across absolute space with no apparent intermediary action-reaction mechanism didn't really fit into Newton's synthesis of classical mechanics, and he had to settle for simply describing gravity's force. This became known as Newton's law of universal gravitation, which states that every object attracts every other object in the universe with a force directly proportional to its mass and inversely proportional to the square of its distance from those objects. For Newton, this must have been like reaching your hand into a black box, feeling an object inside, describing its shape, weight, and texture, but having no idea what the object was. Still, it proved to be an accurate description that worked well enough for classical mechanics over the next 200 years. But then Einstein came along and beat Newton at his own mathematical game. Through the first decade and a half of the 20th century, Einstein went on a mathematical tear, and where his equations led him was to nothing less than the complete overthrow of the classical concepts of absolute space and time, along with gravity. In 1905, he presented his first round of insights, known as his special theory of relativity. Although the math is complicated, Einstein conveyed its meaning with a series of thought experiments that revealed absolute space and time to be merely illusions of one's relative perspective. A common thought experiment was to imagine yourself on a train sitting on a platform right next to another train that's taking up your entire view out the window. Your train begins to move, smoothly but steadily accelerating. You see window after window of the train next to you pass by, and you expect that you'll break out into the sunshine beyond the platform at any moment. But then, all of a sudden, as the last car of the train next to you whirls by, you see the stationary platform out your window, and you realize you weren't actually moving at all. It was the train next to you that was departing. This weird but common experience of relative inertial frames of motion, as it's called, was the first conceptual step toward understanding special relativity. But true insight came when Einstein showed how, as relative motion accelerated in such thought experiments close to the speed of light, the relative values of the apparently universal, absolute constants of classical mechanics like distance, time, and the speed of light changed. Let's say you were on the train that was actually moving. Take away all the windows and accelerate smoothly enough, and you would have no indication whatsoever that you were the one moving. You could accelerate all the way up to nearly the speed of light and still reasonably believe you were sitting stationary on the platform. And here's the key. If you happen to have conducted a series of physics experiments while on that near speed of light traveling train, all of your results would be identical to those of a truly stationary experimenter sitting back on the platform. Even moving close to the speed of light yourself, your measurement of the speed of light, for example, would still be about 300,000 kilometers a second. Relative to the person sitting on the platform, though, your measurement would be 300,000 kilometers a second plus your moving speed, leaving her measurement of your speed of light nearly double her own. Your space and your time are different from hers, revealing that space and time are not really separate at all, but are bound together in their manifestations as something that physicists now think of as space-time. That's special relativity for you, and with it, Einstein demolished the concepts of absolute space and time as distinct entities. But he went even further. In 1916, he introduced a generalized theory of relativity so all-encompassing that it even demolished Newton's concept of gravity. To understand how general relativity did away with the idea of gravity, let's consider a different thought experiment. Suppose that instead of moving inside a windowless train, you were stuck inside an elevator with a friend. Luckily, he brought a ball for you to toss back and forth to pass the time. You each sit down on either side of the elevator and begin tossing it, kind of imagining yourself like Steve McQueen in the cooler in the movie The Great Escape. Now, you have to give the ball a little arc, right, to overcome gravity. So, relative to your perception, that ball travels back and forth between the two of you in a curved line, a parabola. But then, let's imagine that the cable holding up your elevator car snaps, and you begin to free fall. To ward off panic, you just keep on tossing the ball back and forth between you. But now, the effects of gravity are gone, and so you don't need to give the ball any arc. It's like you're floating in the space station, and so you can kind of just push the ball in a straight line across the elevator to your friend, at least according to your perspective. Relative to anyone standing stationary outside the free-falling elevator who could somehow see the path of the ball, it would still be traveling between you two in a curved line. The moment you push the ball towards your friend, you're sailing past the 50th floor, say, and the moment he catches it, you've reached the 48th floor. the path of the ball relative to the perspective of the stationary observer remains parabolic. Straight line for you, curved line for him. The differentiating factor is, of course, something we classically assumed was gravity, but Einstein realized that in a more general sense, it is better thought of, and certainly better described mathematically, as mass, and, quote, the great idea introduced by Einstein was that mass curves space-time. His extraordinary achievement was to find the precise relation between the detailed curvature of space-time and the distribution of mass. With this, he essentially eliminated gravity. We now see that the motion of planets is not the response to a force called gravity, but simply the natural motion of a body along a geodesic in space-time. In other words, motion is a manifestation of geometry. End quote. Since it's so hard to understand how matter curves space-time, the most common visualization is to imagine a big rubber sheet or a trampoline, and now imagine placing a bowling ball on it. The sheet represents the fabric of space-time, and the bowling ball represents a mass like our sun. Now, imagine trying to roll a ball across that sheet in a straight line. This ball could represent the Earth. Its path will curve toward the depression caused by the bowling ball, and depending on its trajectory, it might even become trapped in the bowling ball's orbit and swirl around and around it, like those big funnels that kids roll pennies into. What Einstein was trying to say was that it is more accurate to think of the apparent effects of gravity not as some mysterious force acting at a distance, but as the geometrical distortions to the fabric of space-time caused by mass that deflect objects from uniform motion. All right, so this might all seem too abstract to be of any use at all. It's really almost impossible for us as human beings evolved to perceive 3 dimensions and Euclidean geometry to really understand this. But that's why it's clear that Atkins chose the idea that space-time is curved by matter as his 9th grade idea of science. It was chosen at least in part to make a larger point. Mathematics revealed to Einstein the idea that gravity was just a clumsy stand-in for deeper truth. It might be a convenient stand-in, it might seem sensible, but ultimately it's wrong, and only mathematics is capable of showing why. Becoming more and more comfortable with those mathematics over the past century and confirming their predictions with numerous observational and experimental data, physicists have realized that understanding the geometry of the universe, as opposed to fixating on forces, is the key to understanding its behavior. Or, as some put it, that space-time tells matter how to move, and matter tells space-time how to curve. Atkins' 10th and final great idea of science is a salute to mathematics itself. Quote, "One of the finest creations of the human mind is mathematics, for not only is it the apotheosis of rational thought, but it is also the spine that renders scientific speculation sufficiently rigid to confront experience. Scientific hypotheses themselves are like jelly. They need the rigidity of mathematical formulation if they are to stand up to experimental verification and fit into the network of concepts that constitute physical science. When mathematics confronts the physical world, it sees its own reflection." End quote. Peter Atkins has gone on to write many other books about science since publishing Galileo's Finger in 2004, extending an unrivaled career devoted to conveying the power of science to help humanity transcend ignorance and suffering. A career of championing truth, no matter how odd or inconvenient, and the tools by which we discover it. Not all scientists are so noble. Next time on Context, we'll consider a book that shined a bright light on the dark side of science communication. and revealed how a handful of scientists labored to obscure truth on some of the most important issues of our time. Naomi Oreskes and Eric Conway's Merchants of Doubt. I'm Brad Harris. So long.